Fundación de la Academia de Ciencias de la República Checa. Czech Republic, siempre me equivoco y te digo el antiguo nombre cuando estaban las dos pegadas y le tengo que mirar. Román lleva muchísimos años trabajando en este tema, tiene algunos 120 papers publicados en temas relacionados con data mining y meta learning y learning. Y está de visita aquí porque está en un evento que organizó la rama de IEEE de la Distrital y de la Nacional, que es el tercer World Engineering Application Congress, que tiene varios invitados. Y aprovechando que estaba acá y se nos vino encima, yo vine al meetup del lunes, sí, fue el lunes, y le dije, pues tuvimos un visitante y entonces le comenté a Alejandro y yo dije, pues lo voy a comentar y si está dispuesto hacemos uno y nos quedaron dos pegados en la misma semana, pero era para aprovecharlo porque está hasta el sábado. Ok, you're very welcome.
¿Este evento del AAA tiene algún costo?
El IEEE, el World Engineering Congress, sí, eso tenía un costo, las memorias van a salir publicadas en Springer, es un congreso como internacional, tiene varios invitados, hay de Estados Unidos, de Cuba, México, y hay de toda la región latinoamericana han venido a presentar trabajos. Lo organizan las dos ramas y en este momento ya se acaba mañana, ¿no? Fue ayer, hoy y mañana que tuvieron ahí. Es como transversal, temas de simulación, pero tenían un track muy fuerte en lógica difusa, fuzzy logic and data mining, redes nacionales, hay trabajos de diferentes. De todas maneras, las memorias es posible que tengamos alguna forma de compartirlas, aunque como eso es Springer, eso queda por allá. Pero internamente, de pronto a través de Alejandro, si están interesados en alguna de los papers, a través de algún preprint o algo así, les damos acceso. Yo les envío algún enlace ya cuando esté la información. Viene esta tarde Juan Carlos, que es como la cabeza de la organización de ese trabajo, es un profesor de la Universidad Distrital, porque él es el que mueve eso ahí con los muchachos de IEEE. Bueno, sí, yo voy con
Thank you, muchas gracias. Buenas noches, señoras y señoras. I will be speaking in English because that's pretty much for my Spanish. I know a couple more words. Actually, Germán and Juan Carlos taught me. So it's like una cerveza, dos cerveza, otra cerveza, y claro. It's not really appropriate for this.
The most useful words.
Yeah, café in the morning. Thanks a lot, Alejandro, for arranging this on a sort of short notice. I'm really glad that I can present here. I will be talking for about like 40 minutes, and then we can leave some time for discussion. This is more like I come from academia, right? So maybe some of you come from the real business, working with data. So it would be interesting for me to hear from you what we sort of in this artificial environment, right? We can play with everything. We do not have to really deliver and so on. So nevertheless, it's an interesting. And this is like one of the two best experiences today. The first one was in the morning. I saw the Rio El Dorado. I was in Guatavita, which was also interesting. That's why I'm not really formal dressed, and I might be dirty somewhere or something. Carrying pieces of gold in my pockets. Yeah, so it's called meta learning for data mining. I will be talking about machine learning and then show you some approaches to meta learning. This is a kind of a new subject, very developing. So from some point of view, I would say it's hot and new, but it's not as hot as, for example, deep learning or something. Some people consider it sort of too difficult, too demanding for computational resources and so on. So we are sort of mapping the territory, what approaches are good, what problems we can solve, and I will try to show you some of these. Let's see. Yeah. I'll start with a motivational example. This is the famous Netflix prize. You probably heard of it, right? So it's in 2006 actually, Netflix announced this competition where they have a very simple recommender system for their movies, and they want to improve their system for 10%. So they provide data for the people, right? And at the same time, they said the price is $1 million. So there was, lots of people started doing it because, 10% seems just 10%, right? And $1 million seems, wow, $1 million bucks. So they started, and it actually took them 2.5 years, I think, to be successful, because the first attempts were just not successful at all. They were hardly achieving their level of prediction and so on. The data is sort of tricky because you have users and you have time scale there. The users rank the movies, right? And then you should recommend the movie for the user. More exactly, if you have a pair of a user and a movie, you should tell how many stars the user would give to that movie, right? Based on the previous experience, maybe based on some clustering of similar users and so on. Yeah. So and actually this like team as a Bell Course Pragmatic Chaos, you can even tell from the name that it's like 3 or 4 teams joined together after 2 years, and they finally reached the 10%, the magic 10% improvement. It was sort of an interesting story because roughly at the same time there was another big team that also was doing good progress and contained of several other teams. They were also they have reached the 10% as well. So like half an hour after 3 years, you can imagine one gets $1 million, the other not. So this is sort of a very interesting. But the guys actually didn't keep the $1 million. They donated it because they were from big companies like AT&T and some universities in the US and Europe and so on. So they didn't keep the $1 million. And they couldn't. The Netflix actually couldn't use this solution. They wanted to do another price, but there were some legal issues because the data was not anonymized well enough, basically. So the interesting thing is the solution they provided, right? And it's sort of, you can tell that's why they spent 3 years. It's really not a general solution to anything. What it does, it's like you have around 500 different models applied to different pieces of data. And the models are anything from k-nearest neighbors on different pieces, like on movies, on a time scale. You have the super vector machine somewhere. You have the SVD, single value decomposition, sort of fast linear model, right? And so on and so on. So you have like 500 of them applied to different pieces of data. And they provide sort of features. Like the result of these machine learning models already, they only use to provide features, and then these features are sort of squashed into less features, and then squashed again into less features. This is also like a probabilistic model. So in the end, you have the 500 original features from these methods, the results of the methods already, right? So we can think of pre-processing, but it's very sophisticated pre-processing, and a lot of it. And then you end up in something like 700, 800 different features from different parts, and then you do a simple linear model on this. And then that's how they achieve the 10% improvement. But lots of models here, lots of magic here, lots of magic here. It's really like a tailored solution, and they were working on a solution that's not general at all. During the course of a solution, they actually developed something interesting. They developed a special type of decision tree combined into forests. So there was like an interesting outcome for the science. They provided some kind of general method, a new method how to create those decision forests, ensembles of decision trees. That was sort of interesting. But other than that, the solution is really like very specialized. And so basically we can say that the topic of this talk and maybe a discussion is, can we do this without the people? Can we do this by computer, basically? The answer is not. Not yet, not yet. But I will try to show you what we are trying to achieve, and then I'll show you a similar example that would be much smaller, but sort of interesting as well. Yeah. Yeah, so just briefly, I mean, I don't know how much time should I spend on machine learning. Probably not much, right? Just go through it, and if you think I go too quickly, just let me know, please. Yeah, but I'll be fast here. So this is what machine learning is, and so on. I use an interesting picture. This is from deepr.io. I don't know if you've checked it. This is a deep neural network. Usually the deep neural networks used for pattern analysis are for recognition, if it's hombre or mujer, perro or gato, right, and so on. This type of deepr.io tries to distill some special features that would be different for different painters. So what makes a Van Gogh painting a Van Gogh painting? What makes it different from Gauguin painting or from Picasso painting? It's really difficult, right? We can probably describe something like brush strokes for Van Gogh, right? Energetic brush strokes using lots of blue and yellow and so on. So these guys are able to train the neural network to extract these features, and then you can submit your own picture. This is actually my own picture from Cuba, and looks like Van Gogh, right? So it's sort of interesting to show the capabilities of machine learning models now. Of course, we know machine learning. I like the Peter Flack definition. Peter Flack has a nice book, quite recent, on machine learning that I quite like. The systematic study of algorithms and systems that improve their knowledge or performance with experience. And I really like the experience. I would like to focus on that because meta-learning is basically using machine learning for machine learning itself, right? And the experience there plays a big role. The experience, what does it mean, experience? It usually means that we have lots of data from previous experiments and we are trying to utilize them in a sort of smart way. Yeah. So yeah, this is just, we have some features. We are in machine learning, we are building a model by learning algorithm. The features are sort of abstraction of the real world there, and we have some output. So nothing really special here. A model is what we want to achieve, and we have some learning algorithm and some data. So just to briefly remind, we have three different types of machine learning when we consider a type of feedback: supervised, the most common one probably, right? Classification or regression and so on. Unsupervised is like clustering, dimensional reduction can be there, can be unsupervised and so on. Reinforcement is the most difficult one. It's used in agent learning or robotics. Reinforcement means that you do not have an instant error information, right? As with supervised learning. So usually you just let your robot to sort of run around, you measure the time or something, and then you use some clever algorithm, either some evolutionary type of algorithm or a few learning that's sort of a state-of-the-art for reinforcement learning. Yeah, and then we have the desired output, classification, regression, dimensionality reduction, density estimation, clustering, and so on. It's all pretty obvious. Sometimes people ask me, my students ask me, what's the difference between machine learning and data mining? So machine learning is sort of the core of the data mining. The data mining is probably much more. It's a process that starts with gathering the data, cleaning the data, storing the data, and then thinking of what kind of information I actually want to get from the data, and then how to do it is the machine learning task. But for the machine learning, it's sort of this thing that needs the problem to be specified really well. Like I have to say, this is the data. Sometimes they're nice and clean, like an Excel sheet or something. Sometimes they don't have to be that clean, maybe some data is missing or something. Can deal with that, right? But we really have to formulate it as, this is the problem, it's a supervised problem, or unsupervised problem, or reinforcement learning. This is your data. And now we can split the data into training and testing, do the cross-validation, try whatever you want. Yeah? So there's much more to data mining than just the machine learning. I will focus on the machine learning only. And we really, what we need to do is to be able to formulate the problem as some kind of optimization. Yeah, minimizing loss function, like minimizing an error, for example, right? Usually what we want is the generalization, so we want to minimize the loss function on unseen data, right, on the testing data. Those of you who are working with machine learning models know very well that it's easy to overtrain the model, right? Very easy. And then we're playing with cross-validations and so on to actually make sure that we are providing some model that generalizes well. Yeah. So there's like lots of approaches. I'll skip that. It's just anyway. Yeah, the free lunch. Meta-learning actually has been motivated by the no free lunch theorem, and it's sort of interesting. The no free lunch theorem. You know what? There's this saying about free lunch, right? If you're a girl and a guy invites you for a free lunch, he probably wants something more from you. Yeah, he would probably pay for the lunch, but yes, he wants the girl to pay for the drinks, or I don't know, or vice versa, right? It's just so they're saying there's no free lunch, meaning you will have to pay maybe more than you expect for the free lunch. And so there's actually two versions of the theorem. I only have one here, and I will not go into the detail of the theorem. I just want to sort of explain maybe what is it about. I really like this claim. The no free lunch theorem says that if an algorithm performs well on certain class of problems, then it will have a degraded performance on the set of remaining problems. So this is sort of easy to understand, but the important thing is that the theorem tells that this is true for all algorithms considering all possible problems. Let's not go into detail how do we define, well, an algorithm is actually a way, learning algorithm is actually a way how to represent a function. The problems, well, you can think of some sort of definition of all possible problems. Maybe getting the data by sampling, the training data for the algorithm. And so what we are saying here is that if you want to create a model for your data, and you think probably that a neural network is the best model in the world because you tried a couple times, it was successful, there's no guarantee that it will be good for your new data. Yeah, and actually, I see this problem among my colleagues. They are experts on something. They might be experts on linear algebra, so they very well those linear models, like the fast one. The SVD would be too slow for them, so they have something more clever. So, some other are statisticians, so they like the Bayesian-based approaches. Some of them work with neural networks. And so if you come to them and say, I have this data, what should I try? They say, oh, try neural networks. I'm working on them, I'm an expert. And actually this says that among the models, there's no supermodel, right? There's no one model that would beat them all. It can work very well on certain class of problems, but it will definitely suck on some other problems. Even worse, if you think of it, that one of these valid algorithms is sort of a blind search, or a classifier that would just toss a coin, right? And it means that all algorithms, if you average their performance for all problems, they're as good or as bad as you wish as a blind search or just a random classifier, So that actually sounds pessimistic, right? But the good way how to look at it is, we probably are not interested in having one supermodel that would solve them all, right? It's like Lord of the Rings. But we can actually, if we know that some algorithm performs well on a data, we can, we try to study if it performs well on the similar data. maybe if this algorithm, I don't know, like super vector machines are good for this task, maybe if we find similar tasks, the SVM would be good as well, right? We don't really care that the SVM would suck on totally different problems, right? We can have some other good method there. Yeah. We are not really, in practice, we are not interested unless we really want to be proud of our model and want to show that it's a super model. It's impossible, right? So we are not really interested in that. We are interested in having a good model for our data, So that's nice. Yeah. So what's meta-learning? Meta-learning really is that's the Schmidhuber and Scholl definition. So the process of learning to learn. Yeah, that sounds cool, right? It actually, a meta-learning algorithm uses experience again, right? To change some aspects of learning algorithm or the learning method itself, such that the modified learner is better than the original learner. Yeah. So that's sort of a all-encompassing definition. There are some more theoretical approaches, like the metagenetic programming, the system that is actually evolving the encoding and the operators, more of a theoretical thing. A so-called Gödel machine, that's I think Schmidhuber definition. So it's basically a theorem prover that can modify itself. So the meta part always mean like I will modify myself on the algorithm, but I will modify myself. The genetic programming is really good in it. It's sort of a way how to represent programs. Some theorem provers or Turing machines are sort of easy to be modified as well.
Roman, you talk about experience, but it's quite often that you argue that when you are building just a machine learning model in a particular field or to solve a particular problem, you need experience on the problem.
Yeah.
How that scales out to here? Because I'm guessing that experience that you're talking here is experience building models, not in the field that is the model being applied.
Yeah. So we the experience we are using is really very limited, and it means that we actually have solved a lot of problems by a lot of algorithms, or by the set of our algorithms we are interested in. We know the performance, and when the new data set comes, we are really interested in the most similar data we already solved, and try to get some knowledge from that. Yeah. Okay. So it's sort of now you're a bit skeptical. Right? The experience looks great. This means like looking for similar data sets, basically. Yeah.
So rather than studying the models themselves, you're actually searching just for similar data. That's similar to the one that you already solved.
Yeah, we will probably. Well, I will actually show something like search the properties of a model a bit as well. But it's sort of a thing that I now consider to be like play with the parameters and try to play with the parameters of the model and try to actually find the good parameters. I now consider. So 5 years ago, this was something like wow, but now I consider it that everybody should do it actually. If you have some model and you apply it, you should apply it many times and then try to play with the parameters of the model, because it drastically improves the performance. So I will say something about it, but basically the approach is about the data sets and the performance. So I will be talking about the selection of model for the data. It's really important for the data. It's never universal, right? The no-frills theorem tells us not possible. We're always talking about the data, and something about the model parameter recommendation. I will not talk about the inductive transfer, like transferring knowledge between similar tasks. That would be nice. But we are not working in this area. And so it's actually interesting to differentiate learning from meta-learning by the notion of bias. Right? So in machine learning, a bias is some implicit conditions we are implying to the model. It's probably there by definition, Like for example, if you want to use some linear regression or linear classifier, the implicit condition is that the two classes are linearly separable, right? That's the bias of the model. So we're sort of, we have to know about it, right? For some statistical model, the bias would probably be that you expect the data to have sort of normal distribution and like nice statistical behavior. Yeah, it's the conditions for a model. For some neural networks, if you use them for regression, you probably well, the model has implicit condition that the function you are trying to approximate is smooth, yeah, which probably is not. Definitely not if you sample, right? But the model will provide you with a smooth function. So if the original function is not smooth, you're in trouble, right? Yeah, so this is the implicit condition for a model for bias. So learning always means I'm having one model, so I have a fixed bias. I probably have to think about it in advance, like what bias is good or bad for my data. Is my data really linear? Is my function really smooth? And so on. But meta-learning actually is selecting among the models, so we have the variable bias, depending on the model we are using. Yeah. So the model selection, this is the United States, 1900, the first beauty contest actually. The first beauty contest in the world. So it looks like something like from Charles Chaplin movie. And you see the bias. I mean, yeah, you see the bias. I am a man, so I choose the women. I'm biased. I apologize to women. That's the bias, right? Yeah. So our scenario is that we have the data sets, lots of data sets. The important thing is to have the metadata. That's what properties of the data sets are important. That's the metadata. Yeah. And this is actually, we can discuss this a long time because this is really crucial, and so far we don't know exactly what to use. The traditional approach is that the metadata can be the most simple information you can get from the data set. Something like number of rows, number of your data items, yeah? Number of columns, which means number of features. The type of a task, is it a classification, is it a binary classification, is it a regression, and so on. And then you can think of the individual features or attributes, the individual columns. Maybe you can do some statistics there, right? For each attribute, you can compute the correlations among the inputs, the correlation with the output, maybe some information theoretical measures, but where to stop, right? You can think of computing 10 different numbers for every attribute. If you have something like a image recognition problem, they have their own features that are considered good for the pattern recognition. And so on. So this, like a couple of metadata, is pretty obvious. It can also be seen that they are pretty rough. Like okay, this tells us about the size of a task, so we can say this is big data, this is like toy problem, right? But you can think of the data set that has same number of data items, number of features, and one of the data sets is just a linear problem, another data set is very tricky, very non-linear problem, right? So just computing these numbers doesn't help much. You probably really need to dig into attributes and some statistical properties of the attributes and relationship among attributes. This is really like ongoing research. Well, I'll show you some results. Yeah, and then we have a database of previous results on the models on the data set, and then some kind of procedure how to recommend a new model. In a PDF, this used to be animation, but I will, so I'll do the animation. So you have your data set here, all the data sets, and now a new data set comes. That's this red guy, yeah? Okay. And then you are saying, what method should I use for the new guy? Yeah? And what you do is, you do the two phases, the so-called zooming and ranking. This terminology comes from Pavel Brasdil. He's actually a former Czech guy who immigrated in the 60s to London. Now he's in Porto University. He's an old professor these days. So he speaks about zooming and ranking. So the first phase is zooming. Zooming actually means identifying the near data sets from my database of the data.
Using the metadata.
Using the metadata, exactly. Because actually the metadata defines the space we are dealing with, and now we are talking about the distance based on the metadata. So we want to define a metric on the metadata. So for the few metadatas, like number of rows, number of columns, and type of a task, it's sort of easy. It's like just 3D, and but it doesn't tell you much, right? Yeah. If you consider going to attribute level, then you have a problem because some data have like 3 features, some data have 300 features. So how to deal with that, right? And actually, you can deal with that. This is the easier part. Yeah. The problem is what information about the attributes to choose. Because if you say, okay, the correlations are good, maybe some other statistical moments, maybe some information measure, 1, 2, 3, 4, and then you have 5 numbers for each attribute, 100 attributes, so we end up with 500 numbers describing your data set. So far, so good, maybe it's okay, but I mean, how many data sets you have in your database?
Yeah.
1,000, maybe? Yeah. So it means we are dealing with 500-dimensional space populated by 1,000 points. So even if something is close, it can be pretty different.
And I'm thinking about the features. I mean, the dataset's attributes is because even on an attribute level, you are not going to discover complex. Up to what point you can define complexity of a database by looking at each attribute is quite.
Yeah, that's true. That's true, and it's actually a nice idea. Actually, one of the professors at the conference, Rafael, he's working with rough sets, and they're providing some measure of the complexity of the data for binary classifications based on the rough sets. And actually, you can think of so the rough set is sort of apparatus which I don't understand very well, but you can think of just running something through your data, estimating complexity. I mean, think of this. For example, run a linear classifier or regressor on your data, and if it fails, you can tell this data is nonlinear. That's a good first approximation, right? Then you can think of running sort of more complex but not too complex model. Maybe you can get a class of the complexity of the data based on this. Yeah. So that's one of the things we are actually trying to do the linear thing because it's so cheap. Right? Yeah. So we are doing it even to get some kind of scale for time performance of the models. So yeah. So. But one can think of going much deeper in this, like estimating the complexity of the data. Yeah. So the zooming means that identifying a couple of nearest data sets. Let's pretend we have that. And you see, and we are now going out of the no free lunch theorem curse, because we are sort of, well, hopefully, not guaranteed, but hopefully, right? Because we are omitting all those other guys, all those other data. We are only interested in the, 5 or 10 most closest data sets. And then you, because you have the database of previous results, so on this guy, the multi-layer perceptron was the best, the radial basis function network was the second, and so on. On this guy, the RBF network was the best, the multi-layer perceptron was the second, and so on. So now you somehow gather this information. Brasdil calls it ranking, and basically just ranks it. Yeah, just counts the points and then say, well, our radial basis function network was first. Multi-layer perceptron was second, some kind of regression was the third, so maybe you should try RBF network first, or that's the model recommendation for the new data. Yeah. If it fails, try multi-layer perceptron and so on. When we had a discussion at the Nacional, somebody says, why not try all 3 in sort of ensemble? Yeah. You can do many things actually. The ranking is sort of the most simple thing.
Yeah.
But the idea is you gather information about the performance on the closest data sets and now utilizing the information. What huh?
Is there any centralized site or place where you can actually check if what models you can apply best for your data set specifically?
And I'm glad I can say yes. There is an initiative, European initiative, and they have a site called openml.org. And OpenML, like Open Machine Learning, openml.org. And it tries to gather different data sets and results of different models and describe it in a nice way so you can actually use it. So it's more than, for example, the UCI machine learning repository where you have just the data and so on. And it's a quite new initiative, but they are working very well. We actually, one of my students is cooperating with them, creating some code for different languages and so on. So it's definitely worth looking at if you're interested in it.
OpenML?
OpenML.org. Yeah, so just so I just explained the procedure. These are just some I probably mentioned all of this. Yeah, so the metadata is really a problem. The initial approach is the global metadata proposed by Barsdale. We are now looking at the attribute-based metadata, but as we see, estimating the complexity of the data in some way is crucial. Yeah. Still, it's high-dimensional. We have limited number of samples, and the metadata metric can be. I mean, you can use just a Euclidean type of metric, but you can play with it, And some people even argue you don't have to have a metric. There are some counterexamples from database theory why, for example, the transitivity is not a good property for similarity of strange objects, right? So that's zooming. The ranking really is again selection of a model based on what we see. The best one, King nearest numbers, some kind of clustering. We tried hierarchical clustering. Or, I mean, if you break it up, it's meta-learning, right? So you can train a model on that, right? Actually, the data is not that big for this, so you can play with it, train a model. We actually tried using GP, genetic programming. And,
so the output of the model is which model you should use.
Yeah.
Cool.
Machine learning.
Indeed.
Yeah. Yeah, why not? It's not that crazy. It's not that crazy.
But if you use like that, you multiply as well the error. I mean, if you have an error in the low part, if you go into the meta, you multiply the error as well.
Yeah.
So how you can do that? Even if it works with metrics in the meta model, the metadata.
Yeah. I don't really, I mean, we try to optimize the metrics, but still, yes. Yeah, that's the problem with the approach.
Yes.
But it's sort of like you always focus on a small amount of data, so it's not like a global kind of tragedy, right? It can be bad somewhere, probably will not be bad on other parts. So yeah, but you're right. Those worst case scenarios, they're bad, right? even we can still be in sort of no trick there, right? Yeah. So even what's the suitability criterion? So we are talking now about the classification error or approximation error or regression error, right? But we can think also of considering the time complexity of the learning, because some of these models learn forever, some are fast. It's of a practical importance to be able to say something like that. Maybe even the size of the model. Like right now, the deep networks, they can have like millions of units, which means what? Like megabytes of data. You will probably not feed it into your watch or something, right? So if you use a simple SVM that has like, I don't know, 200 parameters, performs only 10% worse, maybe you should use that, right? So these are also things to consider, like how are you recommending? Yeah. So I will now want to deal quickly about the parameters of the model, and then that's the part that I think is sort of should be standard. So there's nothing special about it. I just say a few things to prepare for showing in one experiment, and that's it. And then I will show you finally Netflix-like results. Yeah. So the parameters of the model, it's really important. Like if you consider, I don't know what kind of libraries are you using, but those models, they're usually nonlinear. They have these strange parameters like convergence rate, momentum value, many parameters. Maybe some of the models, like the super vector machines or some other kernel models, can actually have the kernel as the parameter. And so you don't really know how to start. Maybe you have some default values. Maybe some guy who's working with PCA for 50 years can tell you, oh, I see your data, you should use kappa equals 0.5. But it has to be full moon.
Minutes ago, before you came here, we were talking with Alejandro about his website. You were talking to us about a paper of someone who told that random forest was the best of the best.
A paper of last year in the Journal of Machine Learning Research. The paper was called "Do we need hundreds of classifiers?" Did you read the paper?
No.
So yeah, so it was an interesting paper that at the end it was quite what's the right word? Well, nevertheless, the paper talk about that you should only use random forest, more or less. That was the conclusion of the paper. They run experiments on all the UCI databases and compare hundreds of models, and it was not that the conclusion was not that always random forest was the best, but like 95% of the time, random forest was between 5% margin of error compared with the best models, something like that. So
what percentage?
I have the results somewhere, but the paper is quite interesting to read. But it talk about, they calculate a new metric as percentage of the best accuracy for each database. So for each database, you have what was the best accuracy of any algorithm. So random forest was not always the best, but was almost always very close to the best.
Yeah.
So they talk about it.
So how do we deal with no free lunch theorem?
Indeed.
This looks like we're heading towards a supermodel, right? And it's a random forest. Well, I mean, random forest is a good technique, right? It's an ensemble, sort of by sampling only some special features for each tree. It's sort of robust. I can imagine it can have good properties, right? But
maybe the UCI database is
sort of very biased.
Maybe that's the demonstrations that the UCI is.
Yeah.
Probably.
Yeah. Because it should not be like that, right?
Yeah.
It should not. But I can imagine that for example, what we are using now is the Scikit machine learning toolkit for Python, and the random forests are sort of very successful if you compare with other methods. They're a good starting point, for example. Yeah. And so it's an interesting result. It should not hold generally.
Maybe he was he chose a data that always random forest was one of the best.
Probably. Yeah. So there's these parameters of the random forest. They don't really have many parameters, like 1 or 2, right? So that's also a good point with random forest. But even with toolkits like scikit-learn for Python or some other, you always have some kind of way how to explore the space of parameters of the model. Like usually the grid search is there. So the point was that when we tried, to do at least the grid search for the perimeters, for some values of the perimeters, we always achieved better results. The defaults are really, the problem's usually nonlinear. When you're learning, it's sort of difficult to deal with it, and the setting of the perimeters of the model, like how many units, what's the, I don't know, the convergence rate and momentum for the neural networks, maybe even the type of a kernel for SVMs or other kernel models. So if you can try different ones and do some kind of search on your perimeter space of the model, it's really worth it. It's really worth it. So the grid search is sort of state-of-the-art part of the libraries already. So it means that instead of running your model once, you just run it, I don't know, 100 times or something. The gotcha is that it's sort of exponential, right, in the number of perimeters. So that's a big problem. We tried hill climbing and simulated annealing, sort of local search procedures for the perimeters. We tried evolutionary search, and actually they perform pretty well. Like I will. So what our goal with this is to be able to recommend with the model, to recommend some kind of range of model perimeters. To not the user, only tell him RBF networks are good, try it, but also tell him, well, the Gaussian kernel works best for this neighborhood. Some perimeter k is between 0.1, 0.2, something like that. Yeah. So the workflow recommendation. That's now we're heading towards the Netflix type. So the workflow is a combination of models. We can think of pre-processing. We can think of ensembles and automated ensembles construction. And so that, how do we do it automatically? Well, we are trying to, I will show you some experiments like with automated ensemble construction and some kind of search for more or less general workflow schemes. We are actually using a representation of the schemes by direct acyclic graphs and some kind of genetic programming inspired methods. The problem there is that if you think you have your, I don't know, 20 methods that you can apply, you have probably 10 clustering methods, 10 dimensional reduction methods, 3 or 4 ways how to create an ensemble, bagging, boosting, different types of voting and merging the results and so on. So and then somebody tells you what's the good workflow, how you start. So you can think of putting anything together, and it's sort of correct solution, right? In terms, it's syntactically correct. It can be tried. Maybe it doesn't make sense, but it can be tried. So the problem when you search for a workflow, a combination of models, it's that syntactically you have lots, vast space of combinations of models that are sort of syntactically correct. So yeah, why not try them? But actually, what you want, because you would never find a good solution if you start like this. What you want is that you have sort of constraints there. Some constraints are sort of implicit, some are explicit, and you should also maybe include some preferences based on experience. We are not doing this yet, but it would be nice, because we want to optimize the search. Of course, we want to start from simple models and sort of develop them this way to bigger models, but also to deal with the constraints and maybe have some experience telling like these ensembles were good, these ensembles were not so good, so do not even try them, would really speed up the process. Yeah. So now I will show you some examples, and in the end there's the Netflix-like example. So what we are trying to do was the meta-learning I was telling about the perimeters. So regularization networks, there are sort of kernel networks, linear model of kernel networks using regularization techniques. And we were experimenting with type of a kernel to use. So we were trying to actually use evolutionary algorithm, but quite simple one, to play with the perimeters of the model. And the perimeters of the model are number of units, a type of kernel and maybe some other parameters of a kernel like the width and so on. Yeah? And we found out that it's actually good if we do not do the whole learning by the evolutionary algorithm, because for example, if you have the network, it's got the kernels and then it's a linear combination. So to find the coefficients of the linear combination, it's much better to do some sort of fast linear optimization thing and to not try genetic algorithm, because genetic algorithm is sort of too heavyweight for this. But genetic algorithm helps us recommend the kernels and other parameters. And these networks, actually, they have this nice property that you can think of combination of kernels, either sums or linear combination, or even products. And the products are fun because the product actually splits the input space into two parts and feeds one part into one kernel and another part into a second kernel. And we can use the evolutionary algorithm that actually tells us the split, that tries different splits, and so on. So this was one nice example, and we found out the interesting things that for most of the models, so this is kind of result like the random tree, so the random tree is kind of good. But we found out that actually lots of people are using Gaussian as their first choice, and actually for many problems the Gaussian was not the best choice. The inverse multi-quadric kernel was good. Yeah.
I didn't understand why the multiplying of different models splits the input space in.
Well, that's sort of a property of a kernel model. So you have a kernel, and you feed the data into a kernel, right? It provides some kind of transformation. You're in the kernel space. It's called kernel trick, right? That's the way how you transform non-linear separable problems into linear separable problems, for example. Yeah, like with this special type of networks, it will not work for SVMs, for example. But with this simple neural network that has just the kernels there and a linear combination, you can use the theoretical properties that instead of one kernel, you can use two different kernels, maybe even more. But we're trying just two.
Okay.
And one of the possibilities how to combine them is to do linear combination. The linear combination considers the same inputs into both kernels and sort of adding them together. It provides nice solutions for things like you usually end up with combination of maybe two different kernels, like even like different functions, and one sometimes is like a wider one, sort of covering the broader area, and then one is sort of like this. Yeah. So that's one possibility. The other possibility, from the theoretical properties, you can use a product of kernels.
Yeah.
But the product is like Cartesian product. So you have to have two spaces that are different, and then create a product of them.
Yeah.
Right? And that's why you're using different inputs here, different inputs here. You feed half of the inputs into one kernel, half of the inputs into another kernel, and then you multiply them. Yeah?
So you're not splitting, but combining.
Yeah.
Okay.
But what we need is sort of, that's what I call split, like piece goes to the guy on the left, piece goes to the guy on the right.
Yeah. So the question actually is like, what is that you're gonna feed into the multiplication?
Yeah.
Not the multiplication actually creates the split.
The multiplication actually creates, well, no, what you fit into one part and another part of the multiplication. Yeah, now we understand.
Yeah, all right.
But you can play with it, right? Maybe the data has the property that one kernel is good for, the first, third, and 15th column. Right? Yeah. So kernels are sort of nice because you can have very different kernels for very different things. That's actually the thing behind the convolution network success, right? The deep networks, that you're actually creating your convolution, creating the functions for the task. Yeah. So evolution of ensembles. This was we did with one of my students, and it's actually funny thing. Very simple. Like it's. I just mentioned it because it's possible to do it, basically. So you can think of ensembles, right, of different methods, and you can actually have a simple search algorithm. Here we use really an evolutionary algorithm that would go through your dictionary of models and then create an ensemble, choosing different things, and then we are thinking about the pegging. That sort of we also use one machine learning model to combine the outputs. Another machine learning model, or just say this is voting or averaging, but we say that there can be a small neural network that combines the outputs.
Hey, in practice, what do you use more for that combination part?
Well, it's usually, well, this is an example with sort of limited number of methods. But the neural network was usually the one that was up
On the top.
On the top, yeah. A simple, really, like a one-layer multi-representation. It's enough. It's enough. Usually, it's non-linear already. I don't know.
Yeah. Okay.
Not a big problem. And so with this, we achieved the results that were, of course, it's an ensemble, so it should be better than individual models, but it was even better than some ensembles we tried because we thought they're good. Of course, now you can see that using evolution to create ensembles means that you're actually running it 100 times or something, right? So these are experiments that require 100 times, 1,000 times go through your data at least. Yeah. The parameter search I mentioned already. It's really no magic there. Just use it. This is just an example. We were really interested how genetic algorithms would perform because we are thinking, GA is sort of too heavyweight for this. Like you can use the grid search. Maybe start with some very rough grid, and then maybe optimize on the area that looks promising. We were doing just random search. Simulated annealing actually performs well. It's local, but the simulating part sort of gets it out of the local optima, right? And so this is number of computations we need, and the simulated annealing is interesting, and the GA, that's the full line, is interesting. But it's on different data sets, and usually the GA. If the simulated annealing or a grid search or some kind of very random search performs well, like the simulated annealing was usually good. So we are, so for example here, we achieve a pretty good optimization after like 40 evaluations by simulated annealing. The GA took longer because it's evaluating, but it's a fair comparison, right? We have a small population, so it's really evaluation of the model is the scale. Yeah. So the GA is really good for problems that are sort of tricky. Otherwise, something like simulated annealing is enough. And it should really be done because the error decrease is amazing. Just it can help a lot. Yeah. Now, one example. We are now going into combinations of models. So this is an example. It's actually 4 examples, but this one will do. This is 4 different data sets. And what we did here was that we have this exhaustive search procedure where we're combining together machine learning model with 1 or 2 pre-processings. Just a small example. So we had a set of machine learning models. We had a set of pre-processing. They were basically shrinking the data, shrinking the features, sort of PCA based or random thing, some clustering and so on. And we. The interesting thing was here, because it was sort of fast, just three different models together, 1 model and 2 pre-processing, it was sort of fast. So what we actually did was that we computed not only the error rate, like how good the model performs, but also the time needed for training the model. Yeah. So for example, you have the time in a logarithmic scale here, and you have the error rate here. It's a multi-objective optimization problem, right? So what we can actually do is to provide sort of Pareto front of the non-dominated solution to the user. And now it's up to the user what he wants to choose. So here, the lower the better in terms of performance of the model, right? The left, the better in terms of runtime. So for example, you can see that you have guys here that are very fast, and they're achieving some kind of, I don't know, 0.5, 0.3 error rate. If you want to achieve something better, you have to go here, but it's already like 20 times slower, right? And you're achieving what? I don't know, 10%, maybe 5% only. So this tells you nicely, for this type of problem, it's up to you to choose from these non-dominated solutions. But maybe to achieve a 10% improvement in your error rate, you have to compute 100 times more. Yeah? So what's worth it, right? And it's good because with this was kind of just a linear combination of models. I mean, linear in terms of a chain of 3 boxes together, right? So we have time to compute all the times and everything, and it's sort of interesting to see that it's actually a multi-objective problem. We have this Pareto front, and sometimes really it's like, is it worth it? So because the scale goes to like million times, right? And this is like 1,000 times, 10,000 times, and so on. So it's sort of it actually showed us surprising results. Sometimes you compute something that's like 10,000 times more time, and you achieve just a few percent of improvements. But in linear, it's sort of everybody can do it. Yeah, I will probably skip the attribute selection. That's sort of interesting when we're talking about the distance of the data sets, but I'll skip that. And finally, the Netflix-like solutions. So this is our experiment where we took the different, the name sounds familiar, right? It's from UCI, Machine Learning Repository. So you can say the wine and build sort of middle size, several thousands of examples, classification, features, I don't know, a dozen of features, smaller task probably. And what we are doing here is that we are really creating a solution that has like pre-processing and ensembles and machine learning models together. So the solution is in a form of a direct acyclic graph where we feed the data and it sort of goes just one way. There's no recursion, right? But we can split the data. We can use the pre-processings, we can use the machine learning models here, and then we sort of combine it again. So it always has this kind of direct acyclic graph structure. We are actually using the genetic programming to represent the structures, because you can represent a graph, if it's direct acyclic graph, as a sort of as a tree. Yeah, there's a one-to-one correspondence. And we are actually using a type genetic programming, because there's like different types of data flowing. You have the data, then you might have a predictions because you combine the data with predictions and so on. So we use the type GA. It's only because we want to limit the search space. I told you the search space is big, and anything we can use to limit the search space is good for us. And we have this strategy to start with very small schemes of solutions, like very small, and trying to make them bigger and bigger. So these are the examples where we do sort of for every of these data sets, we did like 65,000 different schemes, train them, use the cross validation, and these are the best models. And so you can see sometimes the best model is really small. Yeah. So sometimes the best model is big, and of course there might be some redundancies or something. We don't know. Maybe it can be smaller. But since we go from smaller to bigger, and we are trying to play with the perimeters and everything, it should be a good model among those 65,000 we tried for each of the data sets. It's sort of sometimes the models make really good sense. If you look here, it's using PCA and an ensemble of 3 methods. They all support vector machines, actually, super vector classifiers, right? And then it's using voting mechanism to do it. So it's simple. For the wine and world, we got crazier solutions. Sometimes we have the copy ensembles. Usually we have ensembles in ensembles, right? Yeah. Some of the ensembles are just copy the data, the same data for the methods. Some ensembles using k-means to split the data, into classifiers. Yeah, that's pretty much it. And you see the decision tree here, support vector classifiers, naive Bayes, Gaussian logarithmic regression. That's pretty much the portfolio. We use the scikit-learn with just a couple of classifiers. So
this is. So is there already a library or something that creates this?
It's a algorithm.
Yeah.
To create. Yeah.
And the library is.
And then we have the library of all the guys. Yeah.
Okay.
Yeah.
No,
with the results.
I think I don't know if that was the question, but if I have a data set, ain't that like just a library that actually tells me, based on your genetic algorithms of different models and stuff, that actually tells me what I should be looking at in terms of what models should be applying, or what structure of models should I apply to my data set?
Yeah. So now we are trying to go from one simple model to more complex solutions. So maybe we can provide, like in this previous example, I forgot to emphasize that this is always a model and one or two pre-processings, right? So in your library, with your results, you don't. All of a sudden, you don't have only like a multi-layer perceptron RBF, but you have a combination of multi-layer perceptron with PCA and k-means.
Okay.
Yeah? And then you recommend probably this scheme. Yeah? So this is just linear, and now we are trying to experiment if we can, do something.
Now you're trying to get it into like a bigger scale,
Yeah.
and see if you can actually achieve a general way, hopefully, of actually judging a database and actually providing the information of what model you should use and parameters and stuff.
Yeah. But there are many open problems, right? The distance of the data, the quality, the complexity of the data, and so on. But still, we can play with it, and this is sort of a nice. But if you compare this to the Netflix, right? It's not like 1,000 of methods.
It's like 500 models.
It's It's not 1,000 or hundreds. It's still 20 or something.
Yeah.
It actually took the evaluation on these data sets. It's like from 1,000 to 10,000 hours on a computer. So it's quite a lot. Of course, we do it on cluster. It's very nice to be distributed, right? It does not depend on you just try the guy. So if you have 100 cores, just do it 100 times, and then you have 100 speed up, and it's just for the weekend or something. Yeah, but still, it's like a lot of computations. But the results are not lost, right? You keep them, and you sort of yeah. So that's actually pretty much it. So we can provide the schemes that sort of look like the Netflix solution that's been, clever guys working for 3 years. It's sort of a general method that can play with pre-processing methods with automated composition of ensembles. And it should be more efficient by applying lots of constraints and heuristics how to actually create them. So now the only heuristics we are using is that we start from small solutions, go to bigger ones, and we have the type system that sort of tell us, no, these two boxes do not fit together.
Okay.
Yeah, so we are not creating obviously wrong solutions. But we are not incorporating some kind of knowledge. I don't know, like ensembles of decision trees are not good, but ensembles of supervector machines are good. Try these first. We are not doing this. This should probably improve this situation. Yeah, so I will probably end here, and I'm ready to discuss it more.
We have time for probably only 2 questions. Or if you want to eat cold pizza, that's up to you.
That's a good motivation. I'll answer shortly.
Thanks for your presentation, Mr. Yu. And I would like to know if you have some examples or application of social science or decision-making process in the organization. And according with this, my question is how we can apply this kind of meta learning in a process, in decision-making process in organization or in the public sector or whatever is social science.
Yeah, it's sort of, as I told you, I'm from academia, so we're sort of playing with data, right? For us, the data is the database we are uploading, but we applied for several practical problems. They were always problems of classification or regression. So if probably if you can formulate your problem as a supervised learning, where you have some kind of examples that you can use for training the model, then it can be used as any other model, because this is sort of just a clever way how to use the models.
Right. Maybe if we can to access to data sets of maybe the behavior of humans related with decision-making process, we can apply in meta learning.
Yeah. One meta information. Let me provide one meta information. I'll be glad if we go to eat pizza. I'll be glad to discuss over email. My email address is very simple. I don't know why it's not there. I'm just stupid. I'm sorry for that. It's roman.neruda@gmail.com. It's roman.neruda@gmail.com. So do not hesitate to write me an email. I'll be really glad to discuss. I see you.
Right. Could you use, when you search for your mental parameters, could you use something like topological data analysis? Because I don't know if you can actually define a distance, but because that's what you use, like a metric distance, but you might be able to define similarity in terms of shape instead of.
In terms of shape, we haven't thought of that. We were playing with the metrics. So for example, we have these attributes and we just put them together and say we're looking for linear combination and we want to enforce the matrix properties. Like you take the axioms of a matrix, the symmetry, the triangle inequality, the transitivity, and we use it in a sort of multi-objective optimization. And so we are providing, for our metadata set, we are providing sort of good metrics. But we haven't thought about the topological properties. That might be a good idea. yeah, thank you.
Have you ever thought about data sets that actually are increasing in size real time? And using your knowledge from the starting data set, so that if I have a second data set that's actually bigger than the first one that has the same components, I don't have to have that computing as much computing power. So we actually update.
That would be great. That would be great. That sort of relates to the inductive transfer, right? Or if you're learning something and you continue the learning, sort of. Yeah, that would be great. We do not consider that, but it would be really interesting.
Okay, so let's thank Roman again.
Muchas gracias. It's been great. Thank you for your attention.